This matrix Xi is the matrix with which Bernd was complaining. Because if the two quantities are not correlated, I will not get anything meaningful into Xi if there is not a correlation. So I might try to correlate the amount of people in this room with the weather outside, and this is not correlated. I still can try, I will see only random noise. And this point made by Bernd is actually very, very important, because what we are doing here is to use the same temporal basis obtained from POD to find the modes of any synchronized data ensemble, which is not sure that will make any sense. And it allows to extract information on correlated events between two quantities. So if the events are not correlated, we don't, of course, we extract only the information that the events are not correlated. So we used this to do an experiment in a high Reynolds number pipe flow. Stefano this morning already told you about the experiment. It is a 130 meters long pipe with almost 90 centimeter diameter. And in this pipe, we put a PIV laser, and we have done PIV, and immediately downstream, we have done measurements with 5 hot wire anemometers. So the goal of this experiment is that we wanted to measure information about large-scale motion into the pipe. We could have done time-resolved PIV, but remember that if data are correlated, you need much more samples to get a good convergence of the statistics. So it was, for our purpose, it was even making much more sense to use PIV in a non-time resolved way, and it was also the only available tool, I have to be honest. So
you seem to have solved a very important experimental problem, because normally the particles which you need for PIV destroy your hot wire sensors. So which particle did you use? So if you find something like microparticles or something like that, at some point they will destroy your hot wire sensors, particularly if the hot wire sensors are downstream.
They were dying here and then, but but not so often as you can imagine. So we could do 2 or 3 hours of test without any death of hot wires.
Cool.
People in Bologna are very good in manufacturing. So the experiment was done having PIV and the hot wire immediately downstream. So what we could have done, what we were thinking about doing, is that we could put the POD of the flow field and correlate the POD of the flow field with among each other. So this method is absolutely not new. A lot of people have done it before. There is also a beautiful paper by Bernd, to cite an example, and Charles Tinney also, and Ewing and Citriniti before. So a lot of people have done what is called the linear stochastic estimation, and then going through the extended POD. So the idea is that, again, we take our PIV fields, which form our snapshot matrix A, and we take our probes, and they form our snapshot matrix. I'm calling P because they are probes. Here, actually, we have a problem that we had only 5 probes. And with 5 probes, we would have got a data set of rank 5, which is not so amazing. Yes?
Why didn't you choose time delay coordinates?
This is what we've done. So we have extracted, at the same time instance of PIV, we have extracted, of course, the probe data. But since we only had 5 probes, what we did is, should we assume that in a little bit of time, the probe is measuring something which was a little bit upstream? So with this approach, we have used some sort of virtual probes obtained assigning data time segments to each PIV snapshot. So we had, for any PIV snapshot, we have a certain amount of hot wire sequence, which was corresponding to this snapshot. And for the first probe snapshot to the last probe snapshot. And The fancy thing is that at any time you have the probe measurements because the hot wire is time resolved. So at any time you can project your hot wire snapshot onto the spatial basis of the hot wires times sigma to the -1, and you get the temporal coefficients of the hot wire POD modes. From these temporal coefficients, through the matrix Xi that we have evaluated before, you can use this matrix Xi to get an estimation of the time coefficient that would reconstruct the flow field at a certain time instant. And finally, you can reconstruct the flow field. What is interesting here, and was pointed out by Bernd before, is that here we have this matrix. The pointer is not really working, but you have the matrix Xi, which is the Greek symbol just on the right of sigma. This matrix looks like this picture here. So it's obviously, you expect that it is more or less diagonal, that the first mode goes well together with the first mode of the probe, the second mode of the PIV goes well together with the second mode of PIV, but it is not, of course, perfectly diagonal. And you also would expect, I guess everybody here would expect, that this matrix Xi goes to 0 if you don't have any correlation, right? Unfortunately, this is not true. This is not true because, and if you say it right, is that you didn't listen carefully, Miguel, before. Because the matrix VA and the matrix VP are both bases in the rank NS. So if I multiply these two bases, what I get is another basis. So I cannot have any vector in nor columns or nor row of the matrix Xi which is not unitary norm and orthogonal to the others. So what happens is that in the matrix Xi, I will have a lot of elements which are very small that probably do not mean anything. But this was actually quite annoying because it was corrupting our reconstruction. And to solve this point, we realized, well, if any row or columns of this data set should have unitary norm, what happens is that, and zero mean because we subtracted the mean before, what happens is that any column and any row of the matrix Xi should have a standard deviation of 1 divided by the square root of the number of samples. And in this case, we could do a sort of filtering, removing all the small values of the matrix Xi, and this was working very well for the reconstruction. So we had these spatial modes, which of course, as discussed by Scott yesterday, were kind of periodic elements in the streamwise direction, which is a direction of homogeneity. We had the first, the second, and the third mode, and we could use this mode to reconstruct the dataset. With three modes, we are reconstructing quite a significant amount of the kinetic energy, which was approximately 50% of the turbulent kinetic energy of the dataset. And we could also estimate the correlation in the, we had a, let's say, a validation dataset with some snapshot that we use only for validation. We could see that we were able to reconstruct the time coefficients of the first, second, and third mode in a quite acceptable way. You can see that for the first mode, you can see that there are some dot elements which are not really close to the line, which means that we were making errors. Yes?
3 modes, 50% of the fluctuation energy of a turbulent pipe flow?
We were in the logarithmic region. We were, I'm cheating a bit, but we are from r equal to 0.1 to r equal to 0.6. So we are in the logarithmic region, and we have large scale motions which dominate the flow. But this is quite in line with what was discussing Javier, because yesterday Javier was telling us that these guys are responsible of 60% of the friction. So not of the rest of the other 40%. But you can realize that with just 5 probes in a very complex flow, because it is a turbulent pipe, it was RE tau, we did at 10 thousandths and 20 thousandths. So in a very complex flow, we could be able to reconstruct the evolution of these large-scale motions. And here, eventually, you have the animation, which also Stefano has been showing you. And you see that the reconstruction is very smooth. You can see the flow is very three-dimensional. You see that some sweeps or ejection are actually entering inside the PIV plane because the flow is very three-dimensional. But there is quite a significant smoothness. And the PIV snapshots were 1 every 4 times. So it is all the rest is reconstructed. So we have also a comparison between a reconstruction of the flow field with the Taylor hypothesis compared on top with the same reconstruction with just the hot wires. Of course, the PIV can allow to complement much this information, this spatial information. This result is extremely interesting, and as Bernd was suggesting, you have to be careful to make sure that quantities are correlated each other. For instance, we have been trying to do the same job, exactly the same, with measurements at the wall, because then if you want to do control, you want to measure at the wall. We have tried to do this with measurement at the wall. I can tell you, there is a poster by Alejandro here, I can tell you that this does not really work well, but because you start having nonlinear relations as anticipated. And in this case, we explored the use of convolutional neural networks, and it works again quite well. So it is important to realize that this tool works whenever you manage to have a correlated data set. In this case, let me go back. It was nice, but you should not really be surprised because we were measuring with the hot wires downstream of our PIV plane. The distance was not that big. Still, the flow was highly three-dimensional, so it was challenging indeed. But of course, if you start measuring in a region which is going to be located farther from your PIV measurement, or you start losing correlation, of course, the result might be worse, and you might need to include some nonlinear effects to improve your reconstruction. Another application of extended POD, which I wanted to present you, is a bit more industrial. So it was inspired by a problem which is very interesting. In Spain, they work a lot on solar power. And I don't know if you know how does it work. It is a lot of mirrors which focus light onto a receiver. This receiver that you see how much it radiates, it gets very hot. And it is made of a huge amount of pipes. These pipes are being circulated by a fluid which is a strange fluid. It's a molten salt. And this salt, it is very nice because it has a very high thermal capacity and it is well suitable for storing the heat and then using to produce electricity. On the other side, you really don't want to have too much thermal variation because you might have chemical reaction in the molten salts, which is not something desired. And also, since you have a pipe in which on one side you are providing a huge heating and on the other side you don't have heating, you also have a problem of thermal stresses and eventually you might destroy the pipe. Yes?
Why isn't one using solar panels? So if you take, for instance, 2 kilometers radius solar panels, you have more. If you have 2 kilometer solar panels, then you generate more energy than a nuclear plant, more than 300 megawatt. So I assume you will only use a fraction of the energy with the mirrors as compared to solar panels.
Yeah, but you don't have the problem of it's another technology, and then it can be stored at night with this fluid which has a huge thermal inertia, as far as I understand.
Can you compare both methods? So what is the fraction of energy you get with this method as compared to solar panels?
I've not done
assume
this.
It's a tiny fraction.
I've not done this. I will do that. I will do that, but I will do that I can give you data if I work on it. But what was interesting is that people in my department decided to do DNS simulation to study this problem. And it was a DNS simulation which heating on one side, sinusoidal heating, maximum on top and 0 on here, and then adiabatic on the other side. So we had a non-uniform boundary condition. And we had well-resolved DNS simulations at 3 Reynolds number and 3 Planck number. So actually, this was air. It was not really a modeling of the molten salt, but it was a bit to understanding this kind of situation, which was quite interesting. And then we had on top a certain temperature distribution, which of course was affected by the heat flux. In this case, we ask ourselves a question: what are the flow structures responsible of the vertical? In this case, it's vertical. I mean, radial turbulent heat transfer in the pipe. So, what are the flow structures responsible of bringing the heat from top to bottom? And in case we want to improve this system, what kind of flow structure should we promote, which maximize the transport of heat for a certain amount of energy? And for this approach, we have used the extended POD, which I was telling you before. Actually, I have to tell you that in this case, the flow quantities are correlated, but not as much as they should be, because in these simulations, the temperature was treated as a passive scalar, for simplicity. But it could have been even more related, because the temperature actually is not a passive scalar. In this case, it would significantly affect the viscosity of the flow. Yes?
Isn't the transfer nearly constant? I was assuming heating on one side, which is nearly constant, and for extended POD, you need a fluctuating quantity, not a steady heating on one side.
Yeah, the heating is constant, but inside of the pipe, the temperature is not constant. So what you are interested in seeing is how the heat goes from the top wall to the bottom wall inside of the pipe. So how do we manage to homogenize the temperature inside of the pipe? What we've done, actually, these are DNS simulations that the Reynolds number was not very high, but still they were not cheap. So what we have done is to take several streamwise planes at a sufficient distance to have sufficient statistical independence. We had 90 instantaneous fields with 50 cross planes, a total of 4,500 snapshots. And the discretization, which was, they gave me the data with a discretization which was 69 radial points and 100 circumferential points. The points were not equally distributed in space. So later on with MATLAB, I will show you how do we do the weighting and how do we build the correlation matrix. So the result is pretty interesting. In this case, the temperature variance has a very different variance distribution along the modes with respect to the flow fields. In the case of the flow fields, the kinetic energy is more or less constant. We have the first modes with less than 3% of the total kinetic energy content. On the other side, we can see that what we have that depending on the Reynolds number and Planck number, depending on the case, we can have up to 7% of energy content in the of variance current, sorry, in the first mode. Also, temperature and velocity modes are very different. Can you tell me how do they should look like the velocity modes? Can you tell somebody? They are Fourier modes in the azimuthal direction.
I would expect something like a dipole mode.
No, the velocity modes are kind of Fourier modes. Of course, to get the Fourier modes that are prescribed by the homogeneity, it will take a lot of samples to reach this good statistical convergence, but still they are Fourier modes in the azimuthal direction.
But you have heating on one side, so this should introduce.
But the temperature is passive scalar.
Yes, but we have heating on one side. So what you are saying, this does not introduce any. It should introduce.
No, because the temperature
passive scalar. Okay.
The temperature is a passive scalar, so the temperature does not affect the velocity. So you could take another simulation of another pipe without heating, and the flow field would be statistically the same. On the other side, of course, the temperature has modes which are more balanced towards the upper side, where you are introducing the heating, and you, of course, there you expect to have more variance. Well, of course, you realize here that flow field is not providing a relevant information for the thermal transport. So this goes back to the discussion before. Whenever we want to analyze a problem, we should choose a decomposition which is relevant to the problem. In this case, the flow field is not providing us any relevant information about the thermal transport. And you see the huge difference between temperature and velocity. This is why we might want to look at the extended modes. So we do the POD of the temperature, we get the temporal correlation matrix of the temperature, and we use this temporal correlation matrix to project the flow field. The temperature is linearly correlated with the velocity because it is being convected by the flow field. And we see here that this is the first temperature mode. This is the corresponding velocity. You have in-plane vector arrows and the contour of the streamwise velocity in the pipe. This is for another Reynolds number and Prandtl number. Of course, increasing the Prandtl number, you have a smaller thermal boundary layer. Increasing the Reynolds number, you have a little bit smaller velocity boundary layer. This is already pretty interesting because this is suggesting you that this kind of flow structure is probably, and then we will see how much, providing a lot of turbulent thermal transport with a little amount of kinetic energy. To be quantitative, we can estimate the heat flux in the vertical direction, so V prime, T prime. And of course, we can get the kinetic energy, the U prime, and the temperature variance T prime, T prime. And we can, most important, get gamma n, which is the vertical heat flux with a reduced number of modes. So it is a low-rank approximation of the heat flux in the vertical direction. And this will be pretty surprising under the engineering point of view, because you see that with only, depending on the case, between 50 and 80 modes, we describe 80% of the heat flux, which is not bad. But even more nicer than this, we can plot the vertical heat flux against the kinetic energy and the temperature variance.